Hybrid orbitals are new types of orbitals that result when atomic orbitals are mixed. For example, carbon's electron configuration is 1s2, 2s2, 2p2. Now what happens with carbon is, if we were to draw like the orbital boxes we've drawn before, like this is the 1s, and we put the arrows in there, and then you have your 2s, and this has 2 electrons as well, and then the 2p, there's 3 boxes for the 2p because it's a p, and I'm going to put 2 arrows in the 2p. Well, what happens is, instead of this being the configuration for carbon, what happens is the 1s stays the same, but the 2s, one of its electrons, is going to move to the 2p. So now my 2p has 3 electrons. And this allows carbon to form hybrid orbitals. Now the hybrid orbital that carbon forms, if you'll notice now, each element that carbon is bonded to can donate an electron here, 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 and here. So like if carbon bonds with hydrogen, hydrogen could put an electron in the 2s and the 2p. And we say that carbon is hybridized sp3. Okay, so where does the sp3 come from? It comes from, there's one available in this s and there's one available in each of the p's. So that's what a hybrid orbital is. It allows carbon to form identical bonds with elements. Okay, that's kind of the theory behind it. Here's what you need to know about hybrid orbitals. The hybrid orbital is just simply how many bonds the central atom forms. So for example, I'll use CH4. CH4 is an example. You draw the Lewis structure for CH4. You do the dots. And you count how many bonds around the central atom. Well, in this case, carbon has 4 bonds around the central atom, and anytime you have 4 bonds, the hybridization is sp3. So I would say carbon in this case is sp3 hybridized, counting the bonds around the central atom. So you draw the Lewis structure and you go back right here to this chart. Let's go through a couple other examples. Let's say I do SO3. SO3. I need to do the dots first, the dot structure. So I would draw SO3, start on the outside, work my way towards the middle. And in this case, this is a particular molecule that's going to have a double bond. But I'm going to do the Lewis structure. And if I want to know the hybridization around the central atom, again, the hybridization is always around the central, you simply count up the number of bonds. There's one here, there's one here, there's one here. And a double bond counts as 1. So I've really only got 3. So I would say sulfur, in this case, is sp2 hybridized because there are 3 bonds around sulfur. Do one more. XeF2. Draw the Lewis structure. This is one of the expanded octets, and you'll notice that xenon has 5 pairs of electrons. Now we do count lone pairs. Lone pairs do count. So there's actually 5 bonds around xenon, 5 pairs of electrons. So I would say the central element, xenon, is hybridized, since there's 5, go back to that chart, sp3d. So really, as long as you know that chart for hybrid orbitals, you will be fine. The number of bonds, it goes 2 through 6. Sigma and pi bonds. Sigma bonds, and the symbol for sigma kind of looks like this. Sigma bonds are formed by head-on or end-to-end overlap of orbitals. I won't try to confuse you with pictures, but there's 2 types of bonds. There's sigma, and then there's pi. Pi is formed by sideways overlap of orbitals. So those are the 2 types of bonds that molecules form. Either they overlap end-to-end or they overlap sideways, and that gives rise to the sigma and pi bonds. So what I want you to know about sigma and pi bonds really boils down to this. All single bonds are sigma. So anytime you have a single bond like CH4, we just do that structure. CH4 was all sigma, all that end-to-end overlap. Every single one of these bonds is a sigma bond. However, if you have a double or a triple bond, let's say CO2, has 2 double bonds. You will have a sigma bond in here, but you will also have a pi bond. So pi bonds only occur when you have multiple bonds. That's the only time you're going to see a pi bond with a double or a triple bond. So really, this is all I want you to know about sigma and pi. Multiple bonds, double and triple, have shorter bond lengths. Triple bonds are stronger than double bonds. That makes sense. And double bonds are stronger than single bonds. But in molecular shapes, we count double and triple bonds as 1 for molecular shapes. Resonance is a concept used to explain how a compound can exist in more than one structured form simply by moving a double bond. Let me give you an example with SO3. And I'm not going to do the dots here. I'm going to try to kind of keep this as neat as possible. Here's SO3. This is also SO3. Now SO3 has a double bond. Just one double bond. But resonance explains how this compound can exist in more than one form by moving a double bond. And you may say, well, these are the same molecule. And you would be right, but let's say I want to label these oxygen. This is oxygen 1, this is oxygen 1, and here's 2, and here's 3. And you'll see that basically the double bond has moved between oxygen 3 and the second structure, it's between oxygen 1 and sulfur. So the double bond has moved. That's a resonant structure. It's the same compound, simply moving that double bond to exhibit resonance. There's actually one more resonance structure I can draw here, and that is if I want to move the double bond between oxygen and sulfur number 2. That would give me my third resonance structure. So when I say resonance structure, it's the same molecule, it's identical molecules, but I'm moving that double bond to give me identical molecules. I'm shifting pi electrons. I'm shifting that double bond. Let me give you one more example of resonance with this compound. It's a ringed structure with carbon in the ring, but there's 3 double bonds in this ring. This is called a conjugated system, where the single and double bonds alternate. It's a conjugated system. But I can exhibit resonance, and that's what this double-sided arrow means, resonance, simply by moving those double bonds. Now, if I move one double bond, I move all double bonds. So a resonance structure would look like this. I moved all 3 double bonds. So this does exhibit resonance, moving pi electrons to give me identical structures, but this is also called a conjugated system because the single and double bonds alternates. Okay, the last big topic on molecular shapes is polarity. Polar bonds are where electrons are shared unequally. And we've kind of went over this before with polar bonds. If it's a polar bond, that means you have 2 different nonmetals bonded together. That's what gives rise to a polar bond. 2 different nonmetals bonded together. The only time it's a nonpolar bond, where the electrons are shared equally, it has to be the same element bonded to itself. So for example, F2 would be a nonpolar bond. But now we're not so much concerned with polar and nonpolar bonds, we're looking at molecules. Polar molecules have a positive end and a negative end, which is called a dipole. Nonpolar molecules do not have this positive and negative end, and there's no dipole with nonpolar molecules. So now we're concerned more with molecules than we are with just the bonds. Okay, a couple big points here. Polarity of a bond is determined by the electronegativity difference of atoms, and I ask you that on the test. So how do you determine if a bond is polar? Look at the electronegativity difference of atoms. How do you tell that a molecule is polar? I'm going to put a star there because that's important. You look at the electronegativity difference of atoms and the shape. So those are 2 big points which are covered on the test. Now, the easy way to tell whether a molecule is polar or not are right here. Number 1, molecules with no lone pairs are nonpolar every single time. Number 2, molecules with lone pairs around the central atom There's two exceptions, square planar and linear, but otherwise they are polar if they have lone pairs. So let me go through a couple examples with polarity here and tell you the easy way to determine polarity. Let's do CCl4. You have to draw the structure. Carbon's in the middle. Chlorine has 7. I'll just draw 1 for chlorine. And then the carbon has 4. So that works out nicely. Okay, I'm simply looking, if I want to determine if it's polar or not, you look around the central atom. Does it have lone pairs? Does carbon have lone pairs? No, carbon does not have lone pairs. So I can tell just by looking it is non-polar. This molecule is non-polar. Does it have polar bonds? Yes, there are polar bonds. Carbon and chlorine have different electronegativities, but the molecule is not polar. Okay, NH3. Again, draw the structure. Nitrogen has 5. If there are lone pairs around the central atom, and there's a lone pair right there, an unshared pair, it is polar. There are two exceptions, but this is not one of the exceptions. This is not the square planar or the linear. This is a trigonal pyramidal. So this has lone pairs. It is polar. One more. XeF2. Drawn this one a couple times before. XeF2. F has 7. We'll just draw 1 there. Xenon has 8. Does the central atom have lone pairs? Yes, the central atom has lone pairs, but this is the exception to the rule. This is the linear with 2 shared and 3 unshared. So even though it does have lone pairs, this is the exception to the rule, so this molecule is actually non-polar.